On to homework 13. Homework 13 here, we've got a couple of questions about separating techniques and then a couple more calculations. Separating techniques are a little bit more straightforward, but having said that, most students get these questions wrong in exams because they've overlooked them in revision and they haven't learned the basics. So that's why it's a good homework to do. Explain how distillation can be used to obtain a sample of drinking water from salt water. As part of your explanation, include a labelled diagram and description of how the particle movement changes with the change of state. Okay, so there's a labelled diagram back in your book, so go look for it if you can't remember what it looks like. Let me just give you a tiny bit of help. I would like you to label a round bottom flask, please. A round bottom flask, that's what we'd have at the bottom of distillation, that's what's going to contain the salt water. You definitely need to label the condenser, because we're going to boil off the salt water. We're going to boil off the water and leave the salt behind, I should say. We're going to boil off the water, and that will be water gas, water vapour. And that water vapour will need turning back into a liquid. It will need condensing again. And that's what the condenser does in this reaction, or not reaction, this process. Of course, it isn't a reaction, this is a physical change. You will also need to label a thermometer. The thermometer is important because it tells us the identity, because every substance has a unique boiling point. It tells us the identity of what is boiling off. In the particle change, we're going to have a particle change from a liquid, where the particles are randomly arranged but yet touching. As we heat them, we're going to give them more energy, so they're going to move faster, and eventually they'll have enough energy to break free from the attractive forces holding them next to their nearest neighbours. When that happens, they've turned to a gas. And then in the condenser, the gas particles are far apart from each other. They're moving rapidly and spaced out. But in the condenser, they're going to cool down, so they're going to move slower and they'll start attracting their nearest neighbours again, turn back to a liquid. So you need to write those in your own words there. Next one is draw a diagram of the apparatus used for chromatography. So chromatography is used to separate a mixture of liquids. It's done on a very small scale, so it uses a piece of filter paper, and we put the dot at the bottom, and we run a solvent up, which is often water when we do this in the lab. And that separates the dyes that make up the ink. Again, there's labelled diagrams earlier in your book. Please go and have a look at those if you can't remember what I'm talking about here. Explain why when using chromatography to analyse different inks that make up a felt tip pen colour, the filter paper needs to be marked in pencil first. The pencil is insoluble. If you mark it in ink, then you're going to you don't know whether you're separating the felt tip pen or the ink that you've marked the paper up with. The solvent front needs marking with pencil line once the filter paper is taken out. So we mark the solvent front because we can calculate the RF value at the end. Now, if we don't mark the solvent front in pencil, the water will dry and we won't see how far the water has run, the solvent has run as time goes by. I'd like you to label as well, please, when you do a diagram, can you label the stationary phase? And the mobile phase. Those terms are important now. They are written in your book when you see them, but I'd like you to label the diagram with which is the stationary and which is the mobile phase. Okay, so we're going to do some formulae of ions here. We've got several ions here. Use them and the periodic table. That's important. Use them and the periodic table to work out the formula of the following compounds. And we've got those to do. Well, I will not going to do any of those, but I am going to do aluminium sulfate. Now, aluminium is not in this table, so we need to use the periodic table. Okay, now remember, the group number tells you the charge on the ion. Okay? The group number tells you the charge on the ion, because if it's in group 1, it's got 1 electron in its outer shell, therefore it forms a 1+ ion. I've already written that in there. I wrote that plus in on a previous video. So lithium forms a 1+ ion, sodium forms a 1+ ion, potassium forms a 1+ ion. Everything in group 2 has got 2 electrons in the outer shell, therefore they all form the 2+ ion. Everything in group 3 has 3 electrons in the outer shell, therefore they form the 3+ ion. Group 4 doesn't form ions, they bond covalently. Coming back the other way, everything in group 0 does not form an ion, so that doesn't have a charge. Everything in group 7 has got 7 electrons in the outer shell, so they form the 1- ion, because they just gain one electron, they gain one negative charge. Everything in group 6 forms a 2 negative ion, everything in group 5 forms a 3 negative ion. Anyway, back to the question. Aluminium sulfate. Find aluminium. There's aluminium, it's in group 3, it forms a 3+ ion. So it's Al3+. Now the sulfate ion is here in the table, SO42-, SO42-. Now to do this, all you need to do is ask yourself one simple question. Are there more positive charges or more negative charges, or are they the same? Okay, because in compounds, the number of positives is always equal to the number of negatives, and we have to get them the same. So you have to ask that question. Are there more positives, more negatives, or are they the same? Here, there are more positives. There's 3 positives and 2 negatives. So we need more negatives. So let's draw a whole nother sulfate ion. Now you have to draw the whole ion. Okay, you can't just draw an S or an O4. Okay, we have to draw the SO4, and that's another 2 minors. So are there more positives or more negatives, or are they the same? We've got 3 positives and 4 negatives, so we've now got more negatives. So we need to draw another positive ion. So we need to draw a whole another Al3+, and that gives us 3 more positive charges. So next same question, are there more positives or more negatives, or are they the same? We've got 6 positives now, 3 and 3 is 6. And we've got 2 and 2 is 4 negatives, so we've got more positives, so we need to draw a whole another sulfate ion. Okay, so now are there more positives, more negatives, or are they the same? 6 positives and 2, 4, 6 negatives, so now they're the same. So now we are balanced. So that's what the aluminium sulfate ionic compound looks like in terms of formula, but we don't write it like that. We need to write it more shorthand now. So how many aluminium ions have we got? We've got 1, 2. So I'm going to write Al2. How many sulfate ions have we got? We've got 1, 2, 3. We've got 3 sulfate ions. So I'm going to write sulfate. I'm going to write SO4. We have to write SO4. That's a sulfate ion. Okay, but we need 3 of them. Now if I just write a 3 there, okay, that means 43. Some people will write SO3. That's horribly wrong. Horribly wrong. What we need, if we've got these complex ions, and we've got more than one of them, that's where brackets come in. If there's only one of them, there's no need for brackets. Okay, but here we've got 1, 2, 3 of them. So I'm going to put 3 outside the brackets, and that is that formula for aluminium sulfate. Okay, you've got 42 on your own. Next question. Okay, now these are quite tricky. Okay, so let's have a go at these. Now the first 2 of these are going to be based around this same formula. So let's write this out. Number, okay, of molecules. The number of molecules equals moles, number of moles, times the Avogadro constant. Okay, so this question says there are 2 moles, okay, 2 moles, times the Avogadro constant, 6.02 times 10 to the 23. Okay, and that would tell you the number of molecules in 2 moles of hydrogen gas. Okay, but the question asks how many atoms. Okay, so that will give you how many molecules. Well, here's a hydrogen molecule. There's 1 hydrogen molecule, an H2 molecule, there it is. Now, a hydrogen molecule contains 2 hydrogen atoms. So whatever answer you get to this, okay, you're going to need to multiply it by 2 because there's 2 hydrogen atoms in a molecule. So this question is quite nasty because, first off, it's got quite a nasty little calculation in it. But then it's even more nasty because it's absolutely essential you know the definition of a molecule and the definition of an atom. Okay, so the molecule is the covalently bonded unit, the H2 molecule. But this question asks how many atoms. So you need to know that an atom is 1 single building block in that molecule, and that molecule has 2 hydrogen atoms. Okay? Next question, how many molecules are present in 2 moles of hydrogen gas? Well, that's just that bit there. So if you work that out there, that tells you how many molecules. Right, turn the page now and you get to your next question. Now, you're going to turn the page. Everything's going to be on your next page, but for some reason my printer's just split this over 2. It won't be like this in your book. Okay, right, so this is now where we are. Next question, what is the mass in grams of 2 molecules of hydrogen gas? Okay, so this really does rely on you understanding about this definition of the Avogadro constant. Okay, let's try and help with that. Right, the Avogadro and the mole, the Avogadro constant and the mole is the same thing. Okay, so 1 mole is the Avogadro constant. It is the name given to a number. Okay, the dozen is the number 12. The Avogadro constant is this number, the mole. 1 mole of anything is this number. So 1 mole of hydrogen molecules. 1 mole of hydrogen molecules. Let's just recap on this. 1 mole of hydrogen molecules. Okay. So a hydrogen molecule is H2, isn't it? There's a hydrogen molecule. Happy with that? Okay, so if we were to work out the mass of 1 mole of hydrogen molecules, we would look at the atomic mass of hydrogen. The atomic mass, the relative atomic mass of hydrogen is 1. So we'd go 1 plus 1 equals 2 grams. Because the mole, or the Avogadro constant, turns the atomic mass into something we can weigh out on a balance. Okay, so hydrogen atoms or hydrogen molecules are ridiculously tiny, so we're going to need loads and loads and loads of atoms before to put on a balance to weigh 2 grams. But that's what the Avogadro constant does. It turns these relative atomic masses into grams. Okay, so we know 1 mole, or the Avogadro constant, is 6.02 times 10 to the 23 molecules, or atoms, or particles, or whatever else. That's what we know it is. Now, that many particles is going to weigh 2 grams. So we need to take our 2 grams and divide it by that Avogadro constant, okay? And that will tell us the mass in grams, and it's going to be really, really tiny because this is a massive number. That will tell us the mass in 1 grams of 1 molecule. So you need to work that out, okay? And that will be the mass, that's going to be the mass in grams of 1 molecule. All right, but the question asks what's the mass in grams of 2 molecules? So whatever that is, you're going to have to multiply it by 2. Right, the next question is extremely similar, but again, it's just testing your knowledge of the word molecule and your knowledge of the word atom. Okay, so in the same way here we did what is the mass in grams of 2 molecules. What we're doing here is what is the mass in grams of 1 hydrogen atom. Let's just work it through again, just to check you're happy with it. So 1 mole of hydrogen, and let's not use molecules this time. Let's use the word atoms. 1 mole of hydrogen atoms. Well, okay, a hydrogen atom is just an H on its own, okay? And a hydrogen atom has a mass number of 1. The relative atomic mass of hydrogen is 1. So if we have 1 mole of hydrogen atoms, it takes that mass number and it takes it into grams, okay? So hydrogen atoms are obviously ridiculously tiny, so we're going to need lots and lots and lots and trillions and trillions of hydrogen atoms before we get it up to 1 gram. But the Avogadro constant, or the mole, that's what it does. So 1 mole equals 6.02 times 10 to the 23 particles. So if we have that many hydrogen atoms, we turn our relative atomic mass into grams. So what we need to do to work out the mass in grams of 1 hydrogen atom is simply to divide 1 gram by that massive number, and it's going to give us a ridiculously small number. Okay, so it's going to be something standard form, but it's going to say to the minus whatever at the end. Work it out, you get an answer. Okay, good luck.